Hi everyone. So this is going to be about the three-body problem. And first of all, I will say that there's ways we can simplify this problem and make it so that we don't need 18 dimensions. For example, we could take the Earth as the center of our coordinate system, which we're free to do, but actually, ironically, that makes it more difficult to describe. So I'm actually just going to do it where we do the full 18-dimensional phase space. Okay, so solving a differential equation means finding a curve through phase space. Now, we often, a curve is usually given by some map, but unfortunately we do not know the formula, and it's impossible to write down a formula analytically for many differential equations. So we don't have a formula. What can we do? Well, we can still think geometrically about approximating that curve. And so that's what this problem's about. Describe the coordinates on phase space R18 when we have the Earth, Moon, and spaceship position and velocities. Okay, so part A. So I'm going to just say in words that position needs 3 coordinates, velocity another 3. We have 3 objects, each needing 6 coordinates. 3 for position, 3 for velocity. So I guess in formulas, I would say that R18 for me, now I'm inventing names. So invent names for all these things. And so I will choose X is sort of roughly position. And V will be velocity. Okay, and then 1 will be the Earth, 2 will be the Moon, and 3 will be the spaceship. So I'm going to order them by their size. But anyway, here we go. So here are the 3 coordinates of the Earth. The Earth will be the first thing, so we have the x11, 12, 13, the first, second, and third coordinates of the position of the Earth. Okay, but we also need the velocity of the Earth. And so that's 6 already. So sort of in a picture, maybe here's my coordinate system, and somewhere over here is x1. And x1 is actually x11, x12, x13, because it is a vector. It's a vector in 3-dimensional space. Somewhere else is the Moon, x2, and somewhere else is our spaceship, x3. In addition, however, the Earth is moving, has some velocity, and the Moon is moving and has a velocity, and the spaceship is moving with some other velocity. I don't know what its velocity will be. And so that's why these numbers, you could maybe make them purple. These 3 numbers correspond to that single arrow, the Earth's velocity at a given moment. Now, the Moon has a position. I've invented variable names for the position of the Moon. And I'll leave some space for the velocity, and now the spaceship has position, and it also needs velocity, so here's the Moon velocity. We'll have those variable names, and finally the spaceship velocity, which I guess would be this arrow. Okay, and so that's my picture. I might as well sort of label these, that this part is the Earth, this part is the Moon, and this part is the ship, or spaceship. Okay, and that's 18 numbers, so we're in R18. Now, is that part A? Describe the coordinates. Good, done. Part B, what are the formulas for the vector field encoding this differential equation? Every ordinary differential equation is a vector field. And so, what's the vector field? So let's answer this one. So, part B. The vector field is, well, like all vector fields, it is a map. It's a map. And what is it a map from? R18 to R18. It is assigning every point in 18-dimensional space a vector. Okay, so what is the formula? So I already have, I could say x11, x12, x13, v11, v12, v13, x21, x22, x23, but I'm not going to. Instead, I'm just going to call this x1, this v1, like that. And this is now going to be called x2 because I'm going to hide detail. Hide detail. It will help me. I need v2, 3 numbers. I need x3 has 3 numbers. And v3 has 3 numbers. And so I could keep going, but I'm not going to. Okay. So now what I have here is a single 18-dimensional vector. So I'll put it in. This just somehow helps me remember that it's an 18-dimensional vector. And now, where does it go? Where is it mapped to? Well, so over here, this vector is basically like how things are changing. It's the differential equation. We'll say, how do things change? So how does the position of the Earth change? Well, by the velocity. How does the position of the moon change? Well, just take the velocity of the moon and put it there. Notice I haven't filled in these ones yet, or these ones. But the position of the spaceship will change by the velocity. So actually, we're halfway done. This part, 9 of the 18 component functions were very easy. So let me get rid of all this clutter. So here I put v1 because the position of the Earth changes by the velocity of the Earth. I don't know what to put there yet. Here I will put v2 because the position of the moon changes by the velocity of the moon. And also v3 because the position of our spaceship will change by the velocity of our spaceship. And now I need the rest. So what do I put here, here, and here? Well, velocity changes by acceleration. And the acceleration will be due, so let's see. Now I'm going to draw a picture to help me figure out what's going on. Let's think about how will the Earth be, or okay, let's start with our spaceship. Our spaceship I think was x3, and the moon is over here. And so the moon is going to pull on our spaceship. And the Earth is going to pull on our spaceship. And so this will be part of the acceleration, and this will be another part of the acceleration. And together they will add to form a sort of a total acceleration. But anyway, this is sort of a cartoon anyways. So let me think. The acceleration due to the Earth, so from Earth, will be final minus initial, this vector. That's at least its direction. So let me normalize that vector so actually we have sort of a unit vector in that direction. And we're going to need some amount of that vector, and then we're going to need some amount of this vector, x2 minus x3. The moon pulls on the ship. and I'll normalize it so that I can think about more carefully what number goes here and here. Okay, so gravitational constant, mass of the moon divided by the square of this distance. Gravitational constant, mass of the Earth. Yes, the Earth is pulling on our spaceship. And x1 minus x3 squared distance. So this is the square of the distance. And that's the formula. Okay, so this piece is from Earth, this piece is from Moon, and together they give the acceleration on the ship. Okay, and that, my friends, goes here. Okay, this is a vector, right? x1 minus x3 is actually a vector. And so this thing will be, a vector filling in how does the velocity of our ship change? Well, it changes by the acceleration. Okay. And this was my picture to help me with that. So let's see what the acceleration, how about of the moon? Well, the velocity changes by the acceleration on the moon. So that acceleration will have, so maybe I'm just gonna, here's our spaceship, here's the moon, x2, here's the Earth. So the acceleration on the moon, well, the spaceship is going to pull on the moon a little bit, and also the Earth will pull on the moon a lot. Okay, so it'll have two contributions. So I will have what the Earth pulls on the moon, plus a vector of sort of in the direction of the spaceship pulling on the moon. So final minus initial. Okay, now these are unit vectors. I made that so that I just get the directions. I need my acceleration to be a vector with 3 components. And so first I just need the directions. Well, one direction is from the ship, one direction is from the Earth pulling. Now how much? It's the gravitational constant. And here this was the Earth pulling, so it's the mass of the Earth. And then divide by the square of the distance. That is a number. And that's how much of this vector. See, this is a linear combination. We're just doing linear combinations again. Gravitational constant, mass of the spaceship, squared. Scalar times vector. Notice that this is basically 0. Because the mass of our spaceship is so small compared to the mass of the Earth, and the mass of the moon. But we'll keep it in there just to be simple, to make everything look the same. Okay, and then the last part is how does the velocity of the Earth change? Well, it changes by some acceleration vector that needs to go there. And the Earth will be pulled towards our spaceship, very small amount, and also towards the moon. So let's do the moon first. Final minus initial is x2 minus x1. And let's just get it to be a unit vector so we can worry about how much in that direction later. Now the ship will pull in the direction final minus initial. And let's normalize to get a unit vector. And now we just have to decide how much of each of these vectors. That is a linear combination. Okay, gravitational constant, mass of the moon, and the square of the distance. Gravitational constant, mass of the spaceship, and the square of the distance is there. Okay, and so I had my pictures to help me. I'll put them over here. And now this whole thing is a vector of 18 component functions. I haven't written out each of them, I instead used vector notation to greatly simplify the formulas here. And a computer has no problem with vector notation, so that's all right. And I'm done with part B. What are the formulas for a vector field? Done. Part C, how do we approximate the solution starting from initial conditions? Okay, so I'm just going to briefly say how to do this. So here's part C. We know positions and velocities at time t equals 0. This means, this means we have a point. We have an initial point. Let's call it P naught, P0, and it's in R18. It's the positions and velocities of the Earth, Moon, and spaceship. Plug into our vector field to get a vector. Okay, V, let's call it V. No, V is bad because it's, what should we call this vector? How about M is bad because mass, these were masses. Oh, to get a vector, P, how about Q? Q in R18. So in particular, like, we literally plug into these formulas with all the initial positions, etc., and we get actual numbers, and we get some actual vector Q. And so let's draw a picture of this. This is obviously a cartoon. Here we are at P0 in R18. And we have Q in R18. Q is this vector. Let's say this vector is Q. Okay, so then what we should do is move a very tiny amount in the direction of Q. And that moves us to this new point, which is P naught plus very small amount, H times Q, for H, a real number, very small. Okay. That gives us our new point. Now, at this new point, P naught HQ, we can plug into our vector field, and we get a different vector. Now we have a new point, so we plug in to our vector field again. This becomes a different vector. It's not Q anymore, it's slightly different than Q. It points in a slightly different direction. So then what we do is we just move a little bit in that direction, and we get to this point. So maybe we'll call this Q0, and then this vector is like maybe Q1, and so maybe this point is P1, which is, or no, maybe this point should be P1. Anyway, the naming of this is not important, so I'm just going to stop. Plug into our vector field to get a vector Q. And I'll say in words, move a very small amount to a new point, P naught plus HQ. So very small H real number amount, and repeat. This approximates the solution curve. The solution curve. Sometimes people call this an integral curve of a differential equation. The solution curve in phase space. Okay? So, what is this new point? This new point has the new positions of the Earth, Moon, and ship. It also has the new velocities of the Earth, Moon, and ship. Every velocity previously got updated by this rule. And because we moved a very, very small amount, this derivative, this vector field, this differential information is pretty accurate. And so even though the true solution curve might look like this, we might sort of follow it like this. And over time we'll get, the error will be worse and worse, but we're roughly following the solution curve. So that's the idea. And here was my answer. Okay, here is the formulas for the vector field. Maybe I should actually say M1, M2, M3 are masses. They're real numbers. And then G is a constant organizing our choice of units, Units are like, did we choose meters or did we choose feet? Did we choose seconds or did we choose weeks? All that sort of information is just lumped together into this capital G. Anyway, that's what physics people do. Very fun. We're all done. Can you solve this? Quiz yourself. How much of this can you do on a blank sheet of paper? This is worth your time. This is pretty awesome.